In this lecture, we will discuss the Unit 2, Slope Deflection Method. In this unit, we have the slope deflection equations, then the equilibrium conditions used to solve the slope deflection equations. Using the slope deflection equations, how to analyze continuous beams and rigid frames, that is indeterminate structures. Then rigid frames with inclined members, then the effect of support settlements and loading conditions, symmetric as well as non-symmetric conditions. First we will see some introduction on slope deflection method. The slope deflection method also is from, that is otherwise, it is a family. Okay, slope deflection method is from the family of displacement method or equilibrium method or stiffness coefficient method. It was proposed by George Manet in 1915 to analyze indeterminate beams and frames. In this method, we express the moments at the ends of a member in terms of its end rotations and translations. That is slope and deflection for a specified external loading. And this method is the base for the moment distribution method and stiffness matrix method. And it is valid only for prismatic member of linearly elastic material subjected to small deformation. That is, shear and axial effects are neglected, not considered in this method. This method is very accurate but tedious, very difficult to solve manually if degree of freedom are more. Now the slope deflection equation. So it is obtained by using the principle of superposition by considering separately the moments developed at each support due to each of the displacement, that is slope and deflection at each end, that is theta A, theta B and delta and external loads. So we get a series of simultaneous equations relating end moments in terms of theta and delta. These equations along with equilibrium equations solved for theta and delta. So once we know the theta and delta, we can easily calculate moments. For portal frames which are non-symmetric in any aspect, additional equations based on shear force is to be considered. To account the sway of the frame. The sign convention used in the slope deflection equation is all clockwise moments and angular displacement, that is clockwise angular displacements, rotations, are taken as positive. Linear displacement, positive when the spans chord angle, the angle of the no span car is clockwise. Here, no, it is shown in green color. Okay, this is the original position AB. After deflection, we get A to B dash. This is the chord. The line joining this A and B dash is the span chord. So how it rotates in this case? No, in clockwise direction. That's why this delta, okay, this delta is positive. So in other words, the right hand side, no support, is lower or below the left hand side support, then that no displacement is considered as positive. Now the derivation of the slope deflection equation, already we pointed out that it is a summation that is using the principle of superposition, all the moments, okay, at the supports due to various conditions, displacement conditions. So the first condition, due to angular displacement theta A, that is rotation at support A. So if you rotate theta A, that is this, if you rotate the support A by theta A amount, then these are the moments created due to this rotation. Okay, so we assume this support B as fixed. This is the hinge. Then only we can rotate the support. Therefore, due to this rotation, MAB, some moment AB is developed at support A, and some moment MBA is developed at support B. So these moments can be computed using moment area method or conjugate B method or any other suitable methods. So we will get moment MAB is equal to 4EI theta A divided by L. Similarly, MBA is equal to 2 times EI theta A by L. That is the, no, here MBA is equal to 4 times EI by theta A by L. Then the opposite side, just half of this moment. Okay, carry over. So therefore 2 by EI theta A. So in this equation we have no stiffness, that's why it is also called as stiffness method. Okay, this is a family of stiffness method. So due to angular displacement theta B at support B, that is, here we consider the support A as fixed, and this is the hinge support. So we allow the support B to rotate by theta B amount in clockwise degree in positive direction. Okay. Therefore, we have some moment MBA, here also MBA. So this the same method. Okay, same principle. Therefore, MBAB is equal to 2 times EI theta B by L. MBA is equal to 4 times EI theta B by L. Now we allow the support B to sink by delta amount. So due to this sink delta, moments are induced at supports at B as well as A. So here MAB is equal to MBA is equal to minus 6 EI delta by L square, because it created negative moment in supports. Then due to external load, we can calculate the support moment, that is called fixed end moment. Moment MFAB, fixed end moment, that AB. Then here fixed moment B. So if we add all the moments at no supports, then we will get the slope deflection equation. So, based on the principle of superposition, if you add all, MAB is equal to 2 EI by L common into 2 theta A plus theta B minus 3 delta by L plus MFAB. Similarly, MPA 2 EI by L theta A plus 2 theta B minus 3 delta by L plus MFBA. So, in this equation, the support where we find the moments will have 2 times rotational effect. So, A means 2A, here B means 2B. Okay, that's the only difference in the expression we have to keep in mind. Now, we will see some fixed moment formula expressions. Okay, so for point load at center, this is the fixed moment induced at support WL by 8, here also WL by 8, and remember the direction. Here in the anti-clockwise direction is a positive direction. Okay, this is negative direction, this is a positive direction. Okay, that is left hand side you will have negative moment, right hand side you will have positive moment. So, if the force acts as eccentric position, then this is the moment W A B squared by L squared, here W A squared B divided by L squared. Then for UDL, this is the moment WL squared by 12. Okay, suppose partly UDL. Okay, then we have this expression WA squared by 12L squared into 6L squared minus 8AL plus 3J squared. Similarly here also. Okay, then uniformly varying load. So, WL squared by 20, here WL squared by 30. This is another case of uniformly varying load. Okay. Then the couple. Couple acts at center. Then we will have M by 4. Here also M by 4. The same direction. Okay. Of the applied moment. See, this is clockwise. So, here also clockwise moment, clockwise moment. Okay. So, this is a shear force or reaction induced. Now, the eccentric couple means this is the expression. Okay. Okay. While drawing the bending moment diagram, this we have to keep in mind. That is, if the moment is negative, then we have to draw the bending moment diagram, that is the points, you have to note the point above, okay, at the left hand side, this one. So, at the left hand side the moment is positive, then we have to draw above the neutral line or elastic center line. Similarly, positive at the right hand side means above the line. Okay, this we have to keep in mind. It is very useful while drawing the bending moment diagram. So, in general, these are the steps involved in analyzing an indeterminate structure using slope deflection method. First, we have to find out the slope deflection equations. We have to formulate. So, while formulating, we have to find out the fixed end moments and support conditions, everything we have to consider. So, once we have the slope deflection equations, then we can go for joining or the combining the slope deflection equation based on equilibrium equations available at each joint. So, from this second step, we will get a series of simultaneous equations. So, once we solve the simultaneous equations, we will get the unknown slope and displacement. So, slope and displacement are found, then we can find out the moments, that is or force. Okay, in the third step. So once we have all the forces or moments, then we can go for drawing bending moment as well as shear force diagram.